Hello, the topic for today's lecture or session is multidimensional signal waveforms and frequency shift keying. However, I will divide this session into two videos, and in this particular video I'm only going to cover the multidimensional signal waveforms topic, and I'll make a separate video for the frequency shift keying topic. Okay, but before we go into the topic of multidimensional signals, let us quickly review what we did in the previous lectures. And if you recall, in the previous lectures, that is 2 weeks back, we talked about one-dimensional signals, and within that we talked about pulse amplitude modulation signals, PAM signals. Okay, and PAM signals being one-dimensional, they are represented using a single basis function, and that means they are represented on a line. So all the signals in the signal space representation are points which lie on the axis, which is nothing but the basis function that represents that particular axis. And then in the last lecture we talked about two-dimensional signals, where we had signals which require two basis functions, or in other words, the signal space representation consists of points in a two-dimensional plane. So there are two orthonormal basis functions, and which represent the two-dimensional plane, and the signals are represented as points in that plane. And for both the cases of one-dimensional and two-dimensional signals, we discussed their baseband versions as well as the passband versions of the signals. So, and we saw how to go from baseband to band pass, and how we did that was to have the baseband signals multiplying a carrier signal of some high frequency, right? So we discussed both the scenarios with baseband as well as band pass for both one-dimensional signals as well as two-dimensional signals. So in the one-dimensional case, we talked about baseband PAM as well as band pass band. Similarly, in the two-dimensional case, we saw a few baseband waveforms, and then we also saw some band pass versions of two-dimensional signals, in which we saw of a few types of band pass signals achieved by means of different modulation techniques, the digital modulation techniques, and some of those were binary phase shift keying, quadrature phase shift keying, QPSK, 8PSK, which are basically carrier phase modulation techniques. And then we also talked about the quadrature amplitude modulation techniques, and in that we saw 4 QAM, 16 QAM, and saw representations of 32 and 64 QAM, and so on. So we've talked about two types of modulations, carrier phase modulation and carrier amplitude modulation, or in fact quadrature amplitude modulation can be having a combination of phase as well as amplitude modulation. Right, and another important observation we made during those analysis is that the bandpass signal energy is half the baseband signal energy. Okay, so we are going to use this concept, use this idea again in the present lecture, and as we go into that, I will be referring to some of the baseband waveforms which we have seen previously for the two-dimensional case, and then extend those ideas to create baseband waveforms in multi-dimensional space. So we'll do it from 2-dimension, we'll take it to 4-dimension, and then extend the ideas further to any m-dimensional space. And then we'll also talk about what is the advantage of having those signals to be orthogonal to each other. Okay, so let's move forward. Okay, so what is a multidimensional signal? Obviously, as the name suggests, multidimensional. That means the signal space representation of such signals would involve multiple basis functions, or the signals are represented as vectors or points in a multidimensional space. Okay, previously when we talked about the modulation schemes in two-dimensional space, which involve two basis functions. We could create m such signal waveforms, right? M could be 2, 4, 8, 16, 32, 64, and so on. But all those signals were in a two-dimensional space, so there are only two basis functions which are orthogonal to each other, and in that two-dimensional space we created m such signals and used them to transmit our data. But because the two dimensions or the basis functions are the only ones which are orthogonal, the signals which can lie anywhere in that two-dimensional plane may not necessarily be orthogonal. They will be orthogonal only if they lie on the axis. For example, if one set of signal lies on one axis and the other set of signal lies on the other axis, then those two signals will be orthogonal to each other. But if there are two signals which lie on the same axis, they will not be orthogonal. And similarly, if there are signals which lie on the same axis, they are also not orthogonal. And if they are lying somewhere in the plane also, they may or may not be orthogonal with respect to each other. What we are interested here is to create m such signals which are all orthogonal with respect to each other. That means we need to have m signals in m dimensions such that each signal lies on its basis function. That means each signal lies on the axis which can be used to represent it. It should lie on the axis which denotes the basis function corresponding to that signal. What is the advantage of doing this, right? The advantage of having orthogonal signals is that it allows us to have a lower bit error probability for a given signal to noise ratio. Okay, so let's look at this. In general, if we want to increase the speed of our communication, then we need to increase the m value for the M array signaling, right? Each pulse for binary, each pulse of duration t represents 1 bit. So if we are transmitting, say, 10 pulses per second, that means the bit rate is 10 bits per second. The same pulses, if we transmit with m equal to 4, then what happens is each pulse or each duration of t seconds would represent 2 bits of information, and that would mean that if 10 pulses are transmitted, that would be 2 into 10, 20 bits per second. So in order to increase the bit rate, we need to increase the value of m. So we have to increase m in order to increase the bit rate. But what we notice is if we have waveforms which are non-orthogonal, as in the case of the two-dimensional signals. So for example, in the two-dimensional signals with 8 PSK or 32 QAM or 64 QAM, there are 32 different signals or 64 different signals or 8 different signals, but they are in the two-dimensional space, so they are not all orthogonal to each other. So in such a case, what happens is, if we plot the bit error probability against the signal to noise ratio, again we have mentioned here the signal to noise ratio per bit, what we notice is, as the value of m is increased from 2 to 4 to 8 to 16 and so on, the probability of error increases for a given signal to noise ratio. So suppose, let's say we have a signal to noise ratio at this point. So we take the signal to noise ratio at this point. So at that signal to noise ratio, as per this diagram, okay, just remember that this diagram is just a reference. These are not actual values, just as a reference to illustrate the situation. So at a particular signal to noise ratio, say suppose this value of signal to noise ratio, with binary transmission, that is for m equal to 2, we achieve a bit error probability of 10 power minus 5. At the same signal to noise ratio, if we move from m equal to 2 to m equal to 4, the probability of error is somewhere here, which is close to 10 power minus 3, which is much higher than the 10 power minus 5. Again, for m equal to 8, it is further higher, and for m equal to 16, it is further higher, right? So the error probability increases with m. So the error probability for the bits increases with m for a given signal to noise ratio. when we use non-orthogonal waveforms, as in the case of our two-dimensional MRE signals, right? This can be viewed in a different way. Rather than saying the error probability increases with m for a particular signal to noise ratio, we can also interpret this in a different way as to achieve a certain bit error probability, what is the signal to noise ratio required for different values of m. Suppose we are interested in having a bit error probability to be below 10 power minus 4. That is, we need to have a bit error probability limited by this value 10 power minus 4. In this case, to achieve 10 power minus 4 bit error probability with m equal to 2, we need a signal to noise ratio given by this point. But for m equal to 4, that is requiring a much higher signal to noise ratio. With m equal to 8, it requires a further higher signal to noise ratio. When with m equal to 16, to achieve the same bit error probability, the signal to noise ratio required is even higher. So we can look at it in two ways. For a given signal to noise ratio, the error probability increases with m, or for a given error probability, the signal to noise ratio required to achieve that error probability increases with m. Alright, so that means to achieve the same error probability, as we go from m equal to 2 to 4, we need a higher signal to noise ratio. That means we'll need to increase the signal power for a given noise power. On the contrary, if you look at the second part of this waveform, the second part of this diagram here, where we have the curves relating the bit error probability with the signal to noise ratio, but in this case the m waveforms or signals that have been used are orthogonal to each other. In the case of orthogonal signals, we see something which is exactly the opposite in behavior to the case when we had non-orthogonal signals. In the case of orthogonal signals, as we increase m, the error probability for a given signal to noise ratio is decreasing. So if you notice here, for m equal to 2, at a particular error signal to noise ratio, let's say we have the signal to noise ratio, let me put it here, okay, at this point. At this signal to noise ratio, m equal to 2 gave an error probability which is close to 10 power minus 1. At the same signal to noise ratio, m equal to 4 is having a lower error probability. M equal to 8 is having even lower, and m equal to 16 is having even lower error probability. So we notice that the error probability decreases with increasing m if we use orthogonal waveform. So this particular diagram here is for m-dimensional orthogonal waveforms. So when our signals are orthogonal with respect to each other, and if we can create m such signals which are all orthogonal with respect to each other, then increasing m gives us an advantage in terms of reducing the signal to noise ratio for achieving a certain bit error probability, or for a given bit error probability, a higher value of m will require a lower signal to noise ratio. So to achieve an error probability, say, of 10 power minus 4, m equal to 2 requires a high signal to noise ratio, m equal to 4 requires this signal to noise ratio, m equal to 8 requires this signal to noise ratio, and m equal to 16 requires a much lower signal to noise ratio. So we can interpret this again in two ways, right? So we can have, for a given signal to noise ratio, the error probability is lower as we increase m in the case of orthogonal waveforms. Okay, if it is not orthogonal, the result is quite the opposite. Increasing m increases the error probability, but with orthogonal waveforms, increasing m decreases the error probability for a given signal to noise ratio, or to achieve a particular target error probability with orthogonal signals, we require a lower signal to noise ratio for a higher value of m. All right, so that gives us like a kind of a power saving for our transmission system, for our transmitter. So that is what we have mentioned here. Okay, so if we have orthogonal signals, then the bit error probability decreases with increasing m, and therefore we can achieve the same error probability with a lower transmission power by increasing the value of m. So therefore it makes sense that we use orthogonal signals to transmit our data. But the problem is to create the orthogonal signals. How do we generate such orthogonal signals? If you want all the signals to be orthogonal to each other, that means we need to have each signal on the axis, and only one signal should be on a particular axis, that is on a particular basis function. So if we have, say, 2 dimensions, then we have 2 signals. Each of the signal lies on the axis, on the x-axis and y-axis, for example. So let me quickly show you. Okay, we'll come to that later anyway. So if we have such m, if we need m such signals, then we need m such dimensions. That means m basis functions which are all orthogonal to each other, and then each signal lies on a particular axis, on that particular basis function. That way we could have m signals which are all orthogonal to each other, because all the signals lie on the axis and all the axes are mutually orthogonal to each other. So because of the error probability advantage we have seen here from a comparison of these diagrams, it makes sense that we use orthogonal waveforms for our transmission. So the question now is how to generate such orthogonal waveforms. So let us have a quick recap of what we did previously. Previously we saw some baseband representations of 2-dimensional orthogonal waveforms. So we had the first representation here of signals S1 and S2 of t, which are orthogonal to each other. How do we know they are orthogonal? Simply compute the inner product S1 integral S1 of t into S2 of t integrated over the interval 0 to t. You will get it as 0, so therefore they are orthogonal to each other. Similarly, S1 dash and S2 dash, if you take the inner product between them, again you will get an inner product of 0, and that means they are orthogonal with respect to each other. Okay, but what you notice here is that these two constructions, okay, this is one set. S1 and S2 is one set of orthogonal signals, and S1 dash and S2 dash is another set of orthogonal signals. The difference between their construction is that the first set, S1 and S2, has an overlapping set of waveforms. So S1 of t and S2 of t are overlapping in the time interval 0 to t. But if you notice the second construction, S1 dash and S2 dash, they are non-overlapping. S1 dash is existing only for this time period, this duration 0 to t by 2, and S2 dash of t exists only from t by 2 to t. So that means the second construction here is non-overlapping in nature as compared to the first construction here, which is overlapping. And it's fairly straightforward that from the observation, the overlapping waveforms, if you want to create overlapping waveforms which are orthogonal to each other, so we start with the first waveform which has a constant value for the entire duration or the time duration that we are interested in for the pulse. The second pulse is created. We want the second pulse to be orthogonal to the first one. So what we do is we keep the same amplitude as A, but we have for half the duration the positive amplitude, and for the remaining half it's negative amplitude. So it's half positive and half the duration is negative over that entire duration t. So that is how we created, or these two waveforms have been created, and it turns out, and you can verify that also, that they are orthogonal to each other. Or the second way is to have non-overlapping waveforms where the entire duration t is divided into the two pulses. Because we are interested only in two waveforms, we divide it into two durations, two equal durations, t by 2 and t by 2. So the first half of that duration t is having the waveform has a certain amplitude, which is a root 2, and the second signal has the same amplitude but for the second half of the duration t, so they are non-overlapping in nature. Okay, why we choose the value to be a root 2, or what is the general rule to decide the amplitude? It's chosen to be to have this value so that the energies of the signals are the same. Okay, we will elaborate that in a little while in the future, in a little while from now, in the next few pages. Okay, so basically we have two ways of creating the orthogonal waveforms. One is the overlapping method, where we start with one pulse and we create the second pulse which has the same amplitude but opposite polarities for half and half of the durations. For half the duration it is having the same polarity as the first signal, and for the second half it is having the opposite polarity as the first signal, right? Okay, let's now extend this idea to create waveforms for m equal to 4. We'll see how to create m equal to 4, that is 4 orthogonal waveforms which are mutually orthogonal with respect to each other, but we'll see how to do it for the overlapping case, and then we'll also see how to do it for the non-overlapping case. Okay, so let's see how to do that. Okay, here again now we have two constructions of orthogonal waveforms for m equal to 4, and in the first construction we have the waveforms to be overlapping in nature. That means the waveforms have values which are overlapping with respect to each other in the entire duration t, and the second construction here is such that the waveforms are not overlapping. There is no overlap between any of the waveforms. They are all non-overlapping in nature. Okay, so if you look at the first one, again we start with a pulse which has a fixed amplitude for the entire duration t. The second signal is created such that for half the duration of the first pulse it is positive, and for the remaining half the duration it is negative. Then to create the third pulse, what we do is we look at the first half of this waveform, and within that interval we make this half positive and half negative, and within the second interval it is half positive and half negative, and that way this waveform would be orthogonal to this as well as this. Okay, so that's one simple way of constructing orthogonal waveforms, and again extend this to the next one. So during this interval, during one pulse interval for S3 of t, S4 of t is having half positive and half negative. Okay, similarly during this particular interval, this is half positive and half negative, and we keep constructing sequences like this, which gives us signals which are orthogonal to each other. Okay, and similarly here we have non-overlapping signals, where we have a duration of t, but since we need 4 signals here, we divide the interval t into 4 parts. So 0 to t by 4, t by 4 to t by 2, t by 2 to 3t by 4, and 3t by 4 to t. So we have divided the interval t into 4 parts. That means each interval is t by 4 durations, and then we choose the amplitude to be 2a. If you recall, for the binary case for m equal to 2, the amplitude is a root 2. For now m equal to 4, it's a root 4. Root 4 is basically 2. In general, for any value of m, when you want to construct non-overlapping orthogonal waveforms, we will set the amplitude of each of this waveform to be a root of m. M in this case is 4, so a root of 4 is 2, so 2a, and the duration of each pulse is t by m, and since m is equal to 4 here, it's t by 4. So likewise we can create non-overlapping orthogonal waveforms for m equal to 8, 16, 32, and so on and so forth. Okay, so now you have some basic idea how to create orthogonal waveforms by the overlapping method as well as the non-overlapping method. Okay, so to generalize the thing, again, before I move further, let me tell you that for our further analysis we will be interested in the non-overlapping waveforms. The reason is because, as you'll see a bit later, the signal space representation of non-overlapping waveforms is such that each of these signals lies on the axis. So S1 dash of t will lie on the axis corresponding to phi 1 of t, the basis function phi 1 of t. The second signal will be a point on the second axis represented by the second basis function phi 2 of t. And since these basis functions are going to be orthogonal, the signals which lie on these basis functions are also orthogonal. So that means each of these signals will lie on a particular basis function and on a particular axis, and on each axis there will be only one signal. So for 4 signals we'll have 4 axes, that is 4-dimensional space, and each axis will contain only one signal. And since all the 4 axes are orthogonal, that means all the 4 signals are also orthogonal. So that is why, because we want to put the signals in the signal space representation to lie on the axis so that we can have orthogonal waveforms. Yeah, and with the non-overlapping case, it becomes much simpler. So we will focus in subsequently and henceforth on the non-overlapping case. Okay, so if we generalize the way of constructing the non-overlapping waveforms, so if you recall, the amplitude for the binary case was a root 2, and it had a duration of t by 2. For the amplitude for the 4 m equal to 4 case is a root 4, which is 2a, and the duration is t by 4. So in general we say that the amplitude of each of the m signals is a root m, and each of them will have a duration of t by m. So the first signal will be from 0 to t by m, and the second will be from t by m to 2t by m, and so on and so forth. But all of them will have the same amplitude a root m, and hence they will all have the same energy. So we see, I put the calculations of the energy here. So you see that each of the signals is energy is s square of t dt. So the value is 2a square, and it is existing only for an interval of t by 4. So each of them has the value of t 2a only for a duration of t by 4. So they all have the same energy, which is a square t. Okay, right, next okay, so that way, once we have the energies, we can now talk about how to construct the basis functions. So the basis functions will be can be obtained using the Gram-Schmidt procedure. And if you recall from the Gram-Schmidt procedure, we need to evaluate the projections of each of those signals onto the basis functions. And since each signal, which is non-overlapping, lies on the basis function, for example, S1 is lying on the axis represented by phi 1, that means the projection of S1 is root e, which is the length, the norm of that signal, but the projection of S1 on phi 2 is 0 because it is perpendicular to phi 2. Similarly, the projection of S2 on phi 1 is 0 since it is lying exactly on the second basis function, right? So with that, what will happen is the Gram-Schmidt procedure will, if you calculate this, you'll get that each of the basis function is simply the signal divided by its norm. So in the case of binary, the signal amplitude is a root 2 divided by the norm, which is the square root of energy, which is a root t. In the case of m equal to 4, the value of each signal is a root 4, which is 2a. So let me go back here. The value of each signal is 2a. Okay, so 2a, but the energies are still the same, which is a square t, and therefore the norm is still a root t. So for m equal to 4, what you will get is the basis function phi 1 will be 2a by a root t, which is 2 by root t, right? But it will have an interval from 0 to t by 4. Okay, in the case of binary, it is root 2 by t for 0 to t by 2 and t by 2 to t. In the case of Fourier, for 4 basis functions or for 4-dimensional space, you will have 4 basis functions, phi 1, phi 2, phi 3 and phi 4, but the values, instead of root 2 by t, it will be root 4 by t, and the intervals will be 0 to t by 4, t by 4 to t by 2, and so on and so forth. Okay, so why this is interesting is choosing the signals to be represented in a non-overlapping fashion means that the signal space representation will have those signals all lying on the axis. So this is the case for the two-dimensional case. So both the signals are on the axis. That means they are going to be orthogonal to each other. And the other thing that you notice from this diagram is that the signals have a distance which is square root of 2e. So you can simply apply Pythagoras theorem to this triangle and get the distance between the 2 points. That gives you the distance between those 2 points, or the distance between the two signals, which turns out to be square root of 2e. So extending this idea, we can now say, okay, since the non-overlapping waveforms when represented in the signal space, they're all points which lie on the axis. So only one of the coordinates will have a value. So if this is two-dimensional space, so the x coordinate has a value which is the norm, and the y coordinate is 0. For the second signal, the x coordinate is 0 and the y coordinate is the norm. So if we extend it to 3 dimensions, then the x coordinate will be the norm, the y and z will be 0. Here the x and z will be 0 and the y will be the norm, and for the third one the x and y will be 0 and z will be the norm, and so on, right? So in that way we can represent we can get the vector representation of m-dimensional orthogonal waveforms to be vectors of m dimensions of length n, where only one of the coordinates is having a value, all the other coordinates are 0. That means the signal S1 lies on the basis function phi 1 at a distance of root e from the origin. The signal S2 lies on the basis function phi 2 at a distance of root e from the origin. So all the signals lie on the basis functions or on the axis of the m-dimensional space. Okay, and clearly if you take the inner product between any two of these vectors, you will notice that they are orthogonal with respect to each other. And the other thing is, even with all the m signals, the distance between any two signals is constant. That means all the signals have mutually equidistant properties. That means the distance between any 2 points or any two signals is square root of 2e. Okay, so that's another interesting property that we notice here. Okay, so it's not possible to depict signals with 4 dimensions on a flat sheet of paper. So what we have here is a representation for 3-dimensional signals. So we have 3 basis functions, phi 1, phi 2 and phi 3. So we have 3 basis functions in 3-dimensional space and 3 signals. Each of the signals S1, S2, S3 lies on the axis. So S1 lies on the axis represented by the first basis function, S2 lies on the axis represented by the second basis function, S3 lies on the axis represented by the third basis function, and all of them have equal energy, and therefore their norm, which is the distance from the origin, is the same, which is square root of the energy, root e. So again, by simple geometry, you can notice that the distance between any 2 points is square root of 2e, square root of 2e, square root of 2e. So basically these are all right angle triangles, and from the right angle triangles you can apply Pythagoras theorem. So this distance is root e, this is root e, so this is root of 2e. So we can see that this can be extended to any value of m, but obviously depicting m greater than 3 on a flat sheet of paper is not so convenient. So we can't see that, but you can anyway feel and intuitively imagine that that is going to be the case, that all the signals will be mutually orthogonal with respect to each other, and all the signals will also have mutually equidistant properties. So it means that the distance between any pair of signals is the same. So between 1 and 2, between 1 and 3, between 2 and 3, all the distances are identical to the square root of 2e. Okay. Now, we talked about these signals as simply non-overlapping signals, but these are a specific kind of signals which are called as pulse position modulated signals, or PPM signals, which is pulse position modulation signals, because the information that we want to convey is contained in the position of the pulse. So let's quickly go back to our waveforms. Okay, if you look at this waveform is a pulse in this position. S2 of t dash is a pulse in a different position. This is the same pulse but in a different position. It's the same pulse in a different position. So all four of them are identical in terms of their amplitude and width. The only difference between them is their positions. So information is contained in the position of the pulse. So this constitutes a kind of baseband representation called as pulse position modulation. Okay, so we call these signals as PPM signals. And the interesting thing about PPM signals is that PPM signals have a geometric representation which are vectors or points lying on the axis of the m-dimensional space. That means they will be orthogonal with respect to each other. So that is the interesting property we are looking towards, because when all the signals are orthogonal, we can increase the value of m and have lower error probability for a given signal to noise ratio. Okay, so we extend that idea to say how do we construct the basis functions. Okay, previously we just said the basis functions is root 2 by t for 0 to t by 2 for the binary case. For Fourier, for m equal to 4, it will be root 4 of t, but 0 to t by 4, and so on. So why that is the case? Because, as I said earlier, the projections are going to be 0 for a particular signal on the other basis functions. So phi 1 of t will lie on, S1 of t lies on phi 1 of t, and therefore the projection of S1 of t on phi 2 of t will be 0, that is, and so on. So if you again look at the Gram-Schmidt procedure, the basic definition for the first basis function is S1 of t by root E1, which is simply S1 of t by root E, because all the signals have equal energy. The second basis function from the Gram-Schmidt procedure is given by this, but since the projection of the second basis function on the second signal S2 on the first basis is 0, S21 is going to be 0 because S2 of t lies on phi 2 of t. So that means this S21 term will disappear, and therefore phi 2 of t will simply be S2 of t by root E2. Similarly, the general equation from the Gram-Schmidt for the third basis function is given by this, and again, because the projection of S3 on phi 1 is 0 and S3 on phi 2 is also 0, so these terms will vanish. So we'll have phi 3 as S3 of t by root E. Okay, so that is basically to say that the basis functions are going to have a particular value of root m by t and for a duration of t by m. Okay, Before we go into the band pass part, I want to give some more illustration of the calculation of the basis functions, just so that it is clear for you guys. Okay, so I'll need to open another. Right. Anyway, the calculations of the basis functions. Okay, I will include that in your notes. Okay, and you can see it for yourself. So each of these signals S1 of t will have an amplitude a root m, but it will all have a fixed energy of a squared t. So by applying that, you will see that the basis functions simply have a value root of m by t. For example, for m equal to 2, it's root 2 by t. For m equal to 4, it is root 4 by t, and the durations will be from 0 to t by m. Okay, t by m to 2t by m, and so on and so forth. Okay, I'll leave it as an exercise for you guys, and you can work it out for yourself. Those calculations are included in the notes, which I will be uploading on Blackboard for you guys, so you can see it and work out and extend the ideas for any value of m. Okay, so I'll stop this particular lecture at this point, and we'll continue this part of the session in a separate video, where we'll extend these ideas to band pass multidimensional signals. So what you have seen so far are baseband multidimensional signals. So we are going to extend this idea to band pass signals, and just to give you a brief introduction, in the case of band pass signals, we are going to simply multiply the baseband signal with a carrier signal, or a carrier of frequency fc, where fc is some high frequency value. So multiply the baseband signal with the carrier signal, that will give you the band pass signal. And what we are going to see is, if we start off with baseband signals which are all orthogonal to each other, the corresponding band pass signals that we generate will also be orthogonal to each other, and so on. So we'll prove those properties, and also see a simple way of producing such multidimensional band pass signals. And in that process, we will see that a simple way of producing multidimensional band pass signals is a technique called frequency shift keying. Okay, so we'll talk about that in the next lecture.